We started yesterday talking about our next topic, which is topic 4, which is bonding. And we started a little bit on ionic bonding, but I want to do a little bit of lecturing, talking about reviewing what we talked about and what you looked at in your study guides yesterday, and then finishing up. There's really not a whole lot on ionic bonding in this topic, so it's something that we spend a lot of time on in honors chemistry with the nomenclature and the balancing the charges, but we're just going to kind of zoom past that here. You got a little bit of a chance to practice that yesterday, a little bit of a chance today, and then we're going to move on to covalent. Okay. So this first, this warm-up question is asking, what are the characteristics of a metal and a non-metal that lead to ionic bonding? So what do you guys think? Edward. Low ionization energy for the metal, high electronegativity for the nonmetal. Raise your hand if you agree with that A is the correct answer here. Yeah. And we'll talk a little bit about why that is today. Just kind of review that. All right, so when we're talking about ionic compounds, a lot of times you can think about crystal structures. Actually have somewhere here. Are they in here? Oh, they might be in the back. I have some crystals from the Rocks and Minerals store at the Natural History Museum, which is like pretty much the best place to go. But what an ionic compound consists of is positive and negatively charged ions, held together in a lattice structure by ionic bonds. So what is an ionic bond? How does that work? Well, sorry, this should be... the sort of shorthand to remember ionic bonding is that it's a transfer of electrons. We've got one element, our nonmetal, or potentially a polyatomic ion, that takes on extra electrons. And that's because it's particularly electronegative. It has a strong attraction for those electrons. The other element, the metal, has a low ionization energy. It's very easy to give up an electron or 2 or 3. And so it's going to give up its electrons. And so what we're going to end up with is a positively charged cation and a negatively charged anion. And the force of attraction is then going to be not so much between the electrons and the protons per se. I mean, it does actually come down to that, of course, but it's the force of attraction between the positive ion and the negative ion that holds these things together. And what you get is a crystal structure, a lattice structure. And so it's the electrostatic attraction between oppositely charged particles. But in this case, the particles are the ions, which can be single atoms or polyatomic. And when we talked about this in honors chemistry, we talked about it in terms of the difference in electronegativity between the elements, which is still true. We're still using that as a sort of cheat sheet for figuring out whether two elements put together are going to form, what kind of bond two elements put together are going to form. It's typically, if we're talking about monoatomic ions, we're talking about metals, nonmetals. And this is something from your data booklet. It's the bonding diagram. It's section 29. You don't have to pull it out, but if you have it handy, feel free. This is kind of like the next level of what we talk about when we talk about bonding types in honors chemistry. So in honors chemistry, we're basically just talking about this axis here, more or less, which is when we're going from ionic to polar covalent to covalent. And we're looking at the electronegativity difference. Okay? So we say if there's a large enough electronegativity difference, then we call the bond between the atoms an ionic bond. And we say that the electron has been transferred completely, or electrons have been transferred completely from one species to the other. And then all the way on the other end, if we have no electronegativity difference between them, if say they're both nitrogens, then we have a non-polar covalent bond where the electrons are shared and they're equally shared. And then, but we set these cutoffs of like, well, if it's more than 1.8 electronegativity difference, then it's probably ionic. But it really is a continuum because the polar covalent is where we have unequal distribution of the electrons. So it's not a complete transfer, but they're not equally shared either. It's somewhere in the middle, depending on how big that difference in electronegativity is. So I used to draw it as like a timeline, sort of, or like a continuum line in 2 dimensions. What I really like about the triangle is that it adds another dimension to it. So it adds this x-axis of average electronegativity. Because if we have no difference in electronegativity, or very little difference in electronegativity, there's actually 2 ways that this could go. We could end up with a non-polar covalent bond if we have 2 very electronegative atoms, both having a strong force of attraction for those bonding electrons. Or we could end up with metallic bonds. If we have 2 atoms that have very low electronegativity, very low ionization energy, both of them just willing to give up the electrons willy-nilly, then we're going to have the metallic structure where we have the lattice of positive ions and the valence electrons are just swimming around, delocalized. Everybody gives up the electrons. So there's really, I like the triangle because it takes the metallic bonding part into account. So if you have low difference in electronegativity, but you also, both of them have a low electronegativity, you're going to end up with a metallic bond. If you have a low difference, but both of them are very electronegative, you're going to end up with a nonpolar covalent bond where they're sharing the electrons, right? And then when the electronegativity difference starts getting higher, then we're moving into the polar covalent or the ionic category, depending on what, where that average is. And even this triangle, I mean, it looks like there are these demarcations between the sections. And of course, it's not like that. It's a continuum. All right, it's shades of gray. We just have to call it at some point. We have to just decide that we're going to lump all these into the ionic category, and we're going to lump all these into the covalent category or the metallic category. And typically, the way we do that is we say if it's a metal and a metal, it's going to be a metallic bond. If it's a non-metal and a non-metal, it's going to be a covalent bond, which could be polar or nonpolar. If it's a metal and a non-metal, it's going to be an ionic bond. So that's kind of the shorthand, but it is actually a little bit more complicated, which is why I like this diagram. Okay, so we went over this already. So I've been talking about this ionic lattice and also metallic lattice structure. And I just want to point out the difference between them. We'll talk a little bit more about metallic bonding later, and we've actually already talked a little bit about metallic bonding in the periodicity topic, but we'll refresh it at the end of this topic. But both types of solid structures have this what's called a lattice structure. It's a crystal structure. It's a organization, a regular organization of the bits and pieces of it. In a metallic system, we've got positively charged ions arranging themselves into this crystal structure with, or this lattice structure, with the electrons just kind of swimming around between them, they're delocalized, they're not really stuck on one atom or the other. And that creates some of the characteristics of metals, like the fact that they conduct electricity, because we have mobile charged particles that can move around. And that is essentially what electricity, what a current is. It's the movement of charged particles. For a solid ionic compound, it also exhibits a lattice structure, but depending on the ratio of the positive and negative ions, you're going to get different shapes. And you don't have to know different shapes. The only lattice structure that you need to know and potentially reproduce, although I've only seen one question ask it in the question bank, but who knows, they could put it on this year's test, is sodium chloride. if you can reproduce the structure of sodium chloride and know that it's alternating positive and negative ions in this sort of cubic structure, you'll be fine. Okay. So you can see that each sodium ion has essentially 6 chloride ions around it in the X, Y, and Z axes, and vice versa for the chloride ions. So it ends up looking like this. Right? And this lattice structure is different because the electrons that make these positively and negatively charged are still localized to the individual ions. All right, so the extra electrons on the negative ions are not just going to float around. They're going to be located on the chlorines. And the sodiums are not just going to be grabbing an electron here and there. They're going to be positively charged. And it's that force of attraction between the positive and the negative that holds the whole structure together. We can also have, we talked about this a little bit yesterday, we can also have these polyatomic ions. And that polyatomic, more than one atom, this consists of covalently bonded atoms that, as a unit, have a charge. So this is sulfate, and it has a negative, the whole thing has a -2 charge. It's not necessarily that negative charge is located in one part of the sulfate ion. If you get further on, beyond the scope of this course, it kind of is. But in general, we treat this as a unit with its own charge for the whole unit. So it has covalent bonding in it, but when it's part of an ionic compound, there's also ionic bonds. So knowing that when we have a compound with polyatomic ions, we have both ionic and covalent bonds involved. It's a frequent question that comes up in paper 1. Okay. I'm not going to get into the resonance yet. We'll talk about that more when we get into Lewis structures. Okay. I'm throwing this up here, and I will post these slides at the end of the day today, because these are some of the ions that you probably should have memorized. Okay, the charge and the formula of these ions. Some of them, they should all look at least vaguely familiar to you from using them in honors chem, writing formulas with them, etc. I don't expect you to have them memorized right now, but it's going to help you a lot if you can make yourself some flashcards and get these memorized by the time of the exam, because even if it's not something that they ask you to recall, just being able to make that mental leap quickly will help you answer the questions faster that involve these. Okay, so nitrate, phosphate, sulfate. Another thing about those 3, and some other ones as well, but these are the ones that are most commonly used, is that they also have a different oxyanion version with 1 fewer oxygens. Still the same charge. It's just 1 oxygen less. And those are going to be the ites. So nitrite, phosphite, sulfite. So the ates have more oxygens, the ites have fewer. If you want to go beyond that, if you look at one of your old honors common ion charts, when you get into the chlorates, there's chlorate, there's chlorite, there's hypochlorite, and then there's perchlorate, because there's lots of different numbers of oxygens. Don't worry about having to memorize that or memorize the names of those, but these are going to be the ites. Hydroxide, you should know, and we're going to talk a lot about it, particularly when we get into acids and bases. Ammonium is one of the only polyatomic cations that you'll be dealing with, and the other one that you come across will really only come across in the context of the acid and base unit, so I'm not going to cover that right now. But you should know the ammonium ion, which is different from the ammonia molecule, which is NH3, which is a neutral molecule. Okay. And again, we'll do like some practice with drawing the Lewis structures of these when we get to that point, and you'll get to see why this is an ion, etc. Carbonate, CO3. And then hydrogen carbonate is also called bicarbonate. You don't need to know that, but it's a slightly older naming convention. And we don't use it much, except it still comes across sometimes for bicarbonate. The IB will use the term hydrogen carbonate. But this is the anion for baking soda. Sodium bicarbonate is, or bicarbonate of soda is sometimes written as baking soda. So that's where that comes in. Okay, so make sure that you know these, that you know how to write them, what the charge is. It'll just make your life easier. We talked a little bit yesterday about writing the formulae of ionic compounds. We talked about the two big things. The charges have to balance to make a neutral compound, and that the ratios have to be the lowest possible ratio between the ions. And so we talked a little bit about these exercises on page 6, I think. Yeah. When you were going through these the other day, were there any particular ones that you had questions about how to write the formula of any of these? One of the questions that came up was about zinc phosphate. One of the questions that came up this morning was zinc phosphate. So number 9, zinc is in the D block. And so you might be thinking, well, why would they give us zinc without a Roman numeral? Because it's in the D block, it should have multiple charges, but it doesn't. The reason it doesn't have multiple charges is that it's at the end of the row of the D block, and therefore it has a full D sublevel of electrons, and those electrons are not going anywhere. So it's only going to form a +2 ion where it gets rid of those 4s electrons. So zinc is always going to be a 2+ ion. That's also something you might want to add to your flashcards. I don't think you'd be in a situation where knowing that it's always 2+ would make or break you, but it's just a good idea. That is something that's part of the HL curriculum as to why it's not. You have to be able to explain it, but just note that zinc only has a 2+ charge. So zinc phosphate, we have knowing what phosphate is, knowing what the charge is. When we crisscross this, if you're doing that shorthand, you're going to end up with ZN3, and then you got to do something with this PO4 to show that you have 2 of them. How do I show that I have 2 phosphates? Parentheses, yeah. Because if I replace this 4 with a 2, then I've completely changed the ion. There is no such ion of PO2. If I put the 2 on the end without the parentheses, then it looks like I have 42 oxygens, which is also very incorrect. So I've got to make sure that and this is part of knowing the polyatomic ions like the back of your hand, knowing that the PO4 is the thing that goes inside the parentheses because that's the unit of the ion, and then you would put the 2 on the outside. Yes? Yes, you would. You would always reduce it to the lowest ratio. So if somehow you had 6 and 4 here, you would reduce it to 3 and 2. Yep. You don't see that very often because we don't usually have that high of a charge on the ions, but at least the ones that you'll have to make compounds with. But yeah, you're always going to reduce it to the lowest possible ratio. And then somebody also asked this morning about number 10, ammonium nitrate. Here we've got 2 polyatomic ions together. And how do we write this together in a compound? Well, the charges happen to already be balanced, so we don't have to worry about parentheses here. Now, if you put parentheses around them, as long as you don't put any subscripts, it wouldn't be wrong. And I don't think they would take points off. I certainly wouldn't take points off if you like put NH4 and then put NO3 in parentheses and took out the charges. I don't think that's not wrong. It's just not generally done. You only use the parentheses if you have more than one. But if it helps you to use the parentheses to keep them separated, to remind yourself in the course of a balancing a reaction or something like that, that they are a unit, feel free. Just know that it's normally not done. Okay. So this is another paper 1 question. So we have a compound consisting of the Ca2 plus ion and the PO4 3 minus ion. What are the name and the formula of that compound? And they give you some options. Name either calcium phosphorus oxide or calcium phosphate. Formulas, a variety of possible formulas. So which would be the correct answer here? Yeah. Yeah, it would be D. Okay, so it's definitely phosphate. So knowing that it's not phosphorus oxide, that's a polyatomic ion that exists as a unit. And then the crisscross gives us the 3 and 2. You have to balance the charges. If we just put it together like that, it's not going to be a neutral compound. The whole compound is going to have a charge of -1. We can't have that. That's not what what's going to happen there. Okay. Okay, so page 9 in your study guide, it goes into some of the properties of ionic compounds that kind of make them how they behave, not in reactions so much, but in terms of their physical properties. We talked about this already a little bit when we were talking about the structures of the period 3 elements and their oxides in the previous topic. But when we're talking about ionic compounds where we have a metal and a nonmetal, like the sodium oxide or magnesium oxide, the melting point and the boiling point are going to be dependent on 2 things, the charge and the radius. So the bigger the charge, the stronger the force of attraction holding these ions together, okay? And holding them in that solid crystal structure. The other thing that's going to affect the force of attraction is the distance. So if we have a smaller ion, is that going to be a stronger force of attraction or a weaker force of attraction? If we have a smaller radius. Yeah? Yeah, it's going to be stronger because the positive charges in the nucleus are going to be closer to the negatively charged ion on the other end, okay? And so it does still come down to the protons and the electrons, even when we're talking about ions as a unit, okay? So smaller ions are going to have stronger forces of attraction, and ions with higher charges are going to have stronger forces of attraction. So if you look at sodium oxide and magnesium oxide, those are right next to each other in the same period on the periodic table. Sodium's a +1, magnesium's a +2. And the melting point for sodium is a little over 1100, and the melting point for magnesium oxide is more than twice that, at about 2800 degrees Celsius. All right, that's degrees Celsius, 2800 degrees Celsius, okay? 100 degrees Celsius is boiling water. All right, so we're talking really, really high temperatures to break these things down because these are relatively small ions, right? The oxygen, sodium, magnesium are all, kind of up there on the periodic table. And so even the sodium oxide where the charge is +1 that's a pretty high melting point. And that is a typical property of ionic compounds. So the melting point tends to be a lot higher than for, say, metallic compounds, and way, way higher than covalent compounds, okay, in general, depending on the structure. So knowing the effective charge and the effective radius on the melting point, and then subsequently also the boiling point. Okay. Solubility is also something that is typically pretty good for ionic compounds in water. This is something we talked about in honors chemistry only in the context of our intermolecular forces, and we talked about the ion dipole attractive force, where we have a positive or negatively charged ion, and then we have a polar molecule like water, where it has a very strong partial positive charge on the hydrogen side and a very strong partial negative charge on the oxygen side of the molecule. And the reason that sodium chloride, for example, dissolves in water is that the positive and negative between two ions, that's a very strong bond. The attraction between the partially positive or negative water molecule, one partially positive or negative water molecule, and the ion is going to be weaker because it's not a full ion. It's only partially positive or partially negative. But if we can get a whole bunch of water molecules around each one of these ions, they're going to separate out, and that's going to swamp the effect of the charges on the charges holding the ionic compounds, the solid ionic compound together. It's going to swamp out that lattice structure, and each individual ion, the sodium ions and the chloride ions, for example, are going to be mobile in a solution, which means something that we'll talk about in a second, but most ionic compounds are soluble in water because water is so polar. Not all of them are, and not all of them are to the same degree. We'll talk about that a little bit more when we circle back around to topic 1. But essentially, it's that strong force of attraction between a polar solvent and the charged ions. So when we're looking at this lattice structure, at this strongly held together lattice of positive and negative ions, by itself, this should have, I thought I got rid of these. The solid compound, if you get one of those like Himalayan salt crystals or something and you stick 2 wires on it and connect them to an outlet, it's not going to conduct electricity. A solid chunk of an ionic compound is not going to be electrically conductive. That is because conductivity requires mobile charged particles, whether it's electrons moving in a wire or ions moving through a solution. So when it's in the solid form, ionic compounds do not conduct electricity. However, if we melt them so that we've broken down that lattice structure, we still have the attractive forces between them holding them together in the liquid form, but now they're able to move. Well, now we can conduct electricity. And then also, if we dissolve them, say in water, we will also get electrical conductivity because now those ions that are surrounded by water molecules can move around within the solution. Okay? And that's why you hear about sports drinks like Gatorade being called electrolyte drinks because they conduct electricity, because there are ionic compounds dissolved in Gatorade. And those are there not so that it can conduct electricity directly. It's because those ions essentially conduct current in your body to make your muscles twitch and your neurons fire and all sorts of other physiological things, which is why when you sweat a lot and you lose a lot of those ions, your performance goes down a little bit if you don't replenish them. So that's what those sort of electrolyte replenishments, or even Pedialyte, if you have been sick and you've been vomiting or something like that, you're also losing a lot of the, you're lowering your concentration of ions, and so that's why drinks like that are used as rehydration, because it's actually going to, there's other reasons for that too, the osmotic pressure in your cells and stuff like that. But so dissolving the ionic compound or melting it will allow it to conduct electricity. If it's fixed in the lattice structure, it cannot. And the last thing is that these compounds tend to be brittle. Metallic compounds, think about your typical like copper wire, something like that. Metallic compounds are malleable. We can beat them into different shapes with a mallet or a hammer, which is what malleable technically means, but we can shape them. We can pull them into wire shape. That's what ductile means. Those are physical properties, malleability, ductility. And those are pretty common in metals. They are not present in ionic compounds. And the reason is it's actually very easy. For as strong as these lattice structures are, it's quite easy for an outside force to break them. Because what's holding them in place is this optimal arrangement of the positive and the negative ions to maximize forces of attraction, minimize forces of repulsion. But if I take a hammer to this and I move one part of it over, now my positive ions are on top of each other, my negative ions are on top of each other, and they don't want to be there. And they're going to repel each other, and we're going to break it off. All right, so that's why you can't shape a Himalayan salt crystal lamp or something. It's not without melting it and then re-solidifying it. It's not going to form a shape other than the natural crystal structure that you're going to see. And if you hit it with a hammer, it's going to shatter. It's not going to bend the way that a similar structure that was made of a metal, just a metal would do. Okay, so that brittleness is because of the repulsive forces between like charges, between negatives and negatives, positives and positives. So when you're answering questions, particularly paper 2 questions on an exam, what you want to do when you're thinking about these physical properties is you want to think about what is the property and what is causing it on a particle level. So the same way that when we talked about periodic trends, we had to think about what is causing this trend in terms of the protons and the electrons in the individual atoms. You want to be thinking about what is causing this property to take place based on what's happening between the positive and negative ions. Okay, so like I said, I'll post these slides. I made this a little bit bigger, but this is basically the same stuff that we just talked about. Soluble in water because of the attraction of the polar molecules to the charged ions. Electrical conductivity only when molten or dissolved. Generally solid at room temperature, high melting and boiling points because of the strength of those attractive forces, and then also the brittleness, that if we can interfere with those attractive forces, we can break it up pretty easily. Okay. All right, and that is it for ionic compounds. So I will put some practice up for naming and formulas so that you guys can practice that both for the polyatomics and just in general, because I know just 10 questions might be enough for some of you to remember how to do this, but you might need a little bit more. And then I also suggest maybe trying to answer some of the questions in the study guide in that section that are more like explanatory questions. Make sure that you can write an explanation, that you know what is an ionic bond, what is the actual force of the bond, etc. So, any questions? All right, we'll move on to covalent stuff next.